So, we're going to talk today about proving trig identities. We introduced several identities recently. We had the three Pythagorean identities. There are some other identities that we should look at, most notably the double angle. That one's going to come up a lot in calculus, is the double angle. But for right now, we actually just want to look at an example of how do we use these things? What do we do with them? And one of the things that we do is we prove an identity. So it'll say something like prove, or it may say show. And then it will give us an equation. Cosine of theta divided by 1 minus sine theta is equal to secant theta plus tangent theta. So the two sides of that equation look pretty different, and yet we're supposed to try to show that they actually equal each other. One of the things that is often done by a lot of students is they tend to work down from this, putting in equals, putting in equals, putting in equals, and trying to manipulate both of the sides until they get to the same thing on both sides. And that, unfortunately, is not a correct approach. You cannot do that. Because, for example, one of the things that you might be tempted to do on this is you might be very tempted to multiply both sides by the same thing, x or blah blah or whatever. Well, what you're using when you multiply both sides of an equation by something is you're using the multiplication property of equality. In other words, you've already assumed that they're equal, and that's not okay. So this is not the approach that we use for proving an identity. The approach that we use is we pick one side or the other and we manipulate it until we get the other side. Just like when you were doing complex fractions and you were trying to simplify them. You didn't start with an equation, you started with an expression and you manipulated it until you got a different expression. In that case, it was hopefully a simpler expression. Here, we're told exactly what expression we're supposed to end up with. But the idea being, you cannot work with it in this equation. You must just pick one side or the other and manipulate it. So, which side do you pick? Well, you can pick either one. My suggestion is to pick the one that's more complicated. But in this situation, it's not as if one is more complicated. One has a fraction in it, which is somewhat complicated. The other one, though, has secant and tangent, which are kind of new to us and therefore also sort of complicated. So we can pick either side. I mean, ultimately, you can pick either side. The idea is they're supposed to be equal. So one way or another, you better get from one side to the other. I'm going to go with the secant theta plus tangent theta. So I start. So on your paper, you know, like for homework or whatever, you would have written this down at the top. You would have that written at the top. That's kind of like your map. That's your guide of where you're headed, but it's not what you start with. You start by writing one side or the other and then manipulating it. You start with one side or the other and then you manipulate it until you get the other side. All right, so we have this here. How am I going to change that? What do you think might be the first change to make in that? Jake? Okay, so change secant into 1 divided by cosine. And if I'm going to do that, what might I also go ahead and do? Break down tangent into sine divided by cosine. And by the way, one of the biggie hints, and I'm going to be giving big hints, I may not have time to write them down, but one of the big hints is to keep looking forward at your roadmap. What do you notice about where you're trying to end here? Do you notice that it only has sines and cosines in it? So probably I need to somehow get rid of secant and tangent, and the easiest way to do that is turn them into sines and cosines. So big hint number one, always use your roadmap, always be looking at where you're headed to give you a clue, a hint about how to change it, how to go next, where to go next. All right, so we've changed the secant and the tangent into sines and cosines. What's the next thing that you maybe see there to do? What's the next thing I might see there? I'll point out that your denominators on these two fractions are the same. How about we add the fractions? Yes, add the fractions. And by the way, look at your roadmap. Do you want two fractions at the end or do you want one fraction at the end? So again, using that roadmap kind of helps give me the next hint. The next hint is if I have two fractions currently and I want one fraction at the end, I obviously better add them. Here we're really lucky they have the same denominator, so I don't even have to do any work to add those two fractions up. So we get to right here, and we've got 1 plus sine theta divided by cosine theta. Wow, but if you look at your roadmap, what's kind of wrong? It's sort of flipped over, and we need a negative, not a positive. So here is the biggie hint that may not occur to you, but it's something you've got to start looking for on proving these trig identities, and that is the idea of conjugates. And we've talked about conjugates before when we were dealing with rationalizing denominators with radical expressions. Same thing. If I look at that numerator and think of it as an a plus b form, then one trick that sometimes works is to multiply by the conjugate, which in this case would be a minus b. But of course I can't multiply by that unless I actually multiply by a special form of 1. So, super secret hint, look for conjugates, multiply by a special form of 1 using conjugates, and we'll see here in just a little bit why we want to do that. So what do I get in the numerator now that I've multiplied a plus b times a minus b? A plus b times a minus b equals a squared minus b squared. Oh my goodness, we should have that by now. We should have had that before we left Algebra 2. Year 2. A plus b times a minus b equals a squared minus b squared. What's a squared in this case? 1. Minus, what is b squared in this case? Sine squared theta. A squared minus b squared is going to give me 1 minus sine squared theta. Now in the denominator you do not want to multiply it out, and we're going to see why, but you kind of had that situation before when we were doing the complex fractions. We said that typically you would not multiply out the denominator because what are you hoping will happen eventually? Some canceling. And canceling can only happen if it's written as multiplication, not if it's distributed and written as addition and subtraction. So just like that, just like the complex fractions work, you're going to leave that denominator as multiplication. Does anybody happen to see something now that is kind of screaming at me, at least? So I got my a squared minus b squared. 1 minus sine squared. 1 minus sine squared. What might that remind us of? Oh, what are we looking at? What do we see there? What might that? One of the Pythagorean identities. Look at your Pythagorean identities. Look at your Pythagorean identities. Remember that we had one that had something to do with sine squared? It also had something to do with a 1? What was that identity? What was that identity? Sine squared plus cosine squared equals 1. That was the original one before we decided to manipulate it and get the other two, right? The original one was sine squared plus cosine squared equals 1. Well, look, if I just subtract over sine squared, I would get that cosine squared equals 1 minus sine squared. Yes? This is why you look for conjugates, is because the Pythagorean identities can always be manipulated into an a squared minus b squared form. Any one of those three Pythagorean identities that we currently have, you can do an a squared minus b squared form, which is therefore going to allow you to make a replacement. 1 minus sine squared can be replaced with cosine squared. So this is big hint number 3, is look for the Pythagorean identities coming into play here. Look for those Pythagorean identities coming into play. Look for those a squared minus b squared forms, which is why we use conjugates quite a bit, because of that a squared minus b squared form showing up in all of the Pythagorean identities. They can all be manipulated somehow to look like an a squared minus b squared. Oh my goodness, what do I see now that I could go and do? I can cancel out one of the cosines, can't I? I have cosine squared in the numerator, I have a cosine in the denominator, and so when I cancel, I get cosine divided by 1 minus sine. Wait, that denominator wasn't supposed to be 1 minus sine squared, was it? Supposed to be just a 1 minus sine. Yep. So we get 1 minus sine theta. Oh my goodness. We did it! Yes, exactly. Look, it looks like the other side. Yes? We started with one side. We manipulated using a lot of tricks, but all good algebra processes, and we were able to end up with the other side. So, to look really mathy now, we're going to add one more thing to this. We're going to add QED. You only get to use QED when it says prove or show, but it makes you look kind of mathy. QED is short for Latin, quod era demonstrandum, that which was to be shown. We showed that which was to be shown. We look mathy. Yay! Now, one of my math teachers said you could also interpret that as quite easily done. But it's a very mathy thing out there to say, I did it. I did what you told me to show. You can't do this when you are asked to solve an equation. You can't do this when it says to find the relative minima or anything like that. You can only put this when it says to prove or show something. But it's kind of a mathy thing. You might even someday have a student give you a mug with QED on it, trying to show how awesome QED is for showing your mathiness. So this is how we deal with trig identities. What were some of the tricks that we talked about here? Conjugates, looking for conjugates. Why? Because the conjugates are going to give us a squared minus b squared forms, which play into the Pythagorean identities. What was another trick? Replacements. How so? All right, so the reason we're looking for those a squared minus b squareds and the Pythagorean identities is so that we can replace things. Just like right here, we replace the 1 minus sine squared with a cosine squared. What's another super secret hint? Yes, always looking back at your roadmap to see where you're headed. And to see things like if I have two fractions at the beginning, but I want one fraction at the end, obviously I need to add the fractions somehow, right? I need to add the fractions. And another hint reminded from the complex fractions work is when you do that special form of 1, don't multiply out the denominator. Sometimes, though, it's going to be don't multiply out the numerator. What it is you're wanting something to cancel. So whatever doesn't give you that a squared minus b squared form is what you're going to work with. All right, I'm going to have to wrap it up because I only get 15 minutes. So that's where we're at. It'll obviously take a lot of practice to work on this, but that's the idea of proving trig identities.